You can see our screen?
Yes, sir.
Yes, sir.
In another 15 seconds.
Yeah, we are live now.
You can start.
In the words of Dr. C.V. Raman, the essence of science is independent thinking, hard work, and not equipment. A very good afternoon to one and all. National Science Day is celebrated on 28th of February every year in order to commemorate the invention of the Raman Effect in India by the Indian physicist Sir Chandrasekhar Venkata Raman on the same day in the year 1928. The main objectives of the celebration of the National Science Day is to make the youth of our country to be aware of the significance of the contributions made by Dr. C.V. Raman towards science and technology, and inspire them to follow his path, and to encourage the junior scientists to popularize science and technology. The theme for this year's National Science Day is Future of Science, Technology and Innovation, Impacts of Education, Skills and Work. On behalf of our Principal Ma'am, Mr. Shailaja Gopinath, Headmistress Ma'am, Wing in Charge Ma'am, teachers, and students of DPS Secunderabad, it gives me immense pleasure to welcome Professor S N Hasan, MPhil, PhD in Mathematics, who will enhance our knowledge on the discovery of Raman Effect by popular Nobel laureate Dr. C.V. Raman, and Dr. Priya Hassan, an astrophysicist, who will enrich us with an exciting and informative session on the latest Indian space programs. We extend you a very warm welcome, ma'am and sir. We are greatly honored to have you in our midst.
Dr. Priya Hassan did her integrated master's in physics, specializing in astrophysics from the Moscow State University, Moscow, Russia in 1996. She did her PhD in astronomy at Osmania University, Hyderabad in 2004. She did her postdoctoral research in France and IUCAA Pune. She was awarded the Women Scientist Award by Department of Science and Technology, New Delhi in 2006. The US Consulate, Hyderabad, selected her for the International Visitors Leadership Program in 2011 to visit and deliver lectures at selected universities in US. Her research interests are in observational astronomy, star formation, star clusters, and galaxies. At present, she collaborates with groups in India, Europe, US, and Egypt, and has recently visited the Harvard Smithsonian Center for Astrophysics, Cambridge, USA, on a summer internship program of the International Astronomical Union. She is a member of the International Science-driven team of the 30-meter telescope. She is actively involved in Olympiads, public outreach, and science popularization programs for children and adults. At present, she is an assistant professor in physics at the Maulana Azad National Urdu University, Hyderabad. She is also the secretary of the Public Outreach and Education Committee, Astronomical Society of India.
Professor S N Hasan was the head of the Department of Mathematics and Dean, School of Sciences, Maulana Azad National Urdu University. Before joining this university, he was head of the Department of Astronomy, Osmania University, Hyderabad, and director of the Japal Rangapur Observatory. He completed his MSc and MPhil at the University of Hyderabad and PhD at the Moscow State University and has more than 25 years of teaching experience. He is actively involved in Olympiads, public outreach, and science popularization programs for children and adults. We extend you a very warm welcome, ma'am and sir. We are greatly honored to have you in our midst. So without further ado, let me take the privilege of inviting our esteemed speakers. Ma'am, please. Sir, please.
Thank you.
Thank you. Thank you for your introduction and kind words. And thank you for giving us an opportunity to talk to the young minds. They are the future of science and future of India. And it's always a pleasure talking to children. Sriram, National Science Day in India is celebrated on 28th of February to commemorate Raman's works on the scattering of light, which is known as the Raman Effect. So I'll be talking about light, what is spectra, the Raman Effect and its applications. India, as you all know, has a very successful space program, and she'll take you through that. So here it is. This is the day we celebrate the work of Raman, and he was the first Asian in 1930 to get a Nobel Prize in Sciences, and he was the second Nobel Prize winner for, oh, we have come out.
I think there's a connection.
There is connection problem. Can you hear?
Yes, sir, we can hear you.
Oh, it appeared that okay, so we'll come to this. What is light? And we have works of Newton and Huygens. Both of them lived around the same time. So Isaac Newton, 1643 to 1727, and Huygens, 1629 to 1695. They had two views about what is light, what is the nature of light. Isaac Newton believed that light is transported by corpuscles, small particles which carry the charge and which carry the radiation, and this was called the corpuscular theory of light. While Huygens believed that light travels from one point to another, that energy is transported through waves. He had the wave theory of light. And what we see today is both of them were right, and there are certain phenomena of light which we see, and so that we try to understand what is the basic nature of light. And the important ones which I shall be referring to you in this small brief, and scattering again is another feature which we are interested in, particularly today when we are talking about Raman's works. So present understanding of light is that light travels from the source to its destination by very small particles called the photons. So Newton was right, but these photons, they have a dual nature. This is called the wave particle duality. They behave like particles at a certain scale, and they behave like waves. There's certain phenomena of light which is very typically of how it behaves, that can be well explained by the particle nature. So what it appears is both the intuitions of the great men was right. Huygens was right in his own way, and so was Newton. So, and we are familiar with Newton's work with the spectra of light. He had used prisms to split the white light into a rainbow of colors. I hope you have done this in your laboratories. If you take a prism which is shown you in the screen, and you focus a beam of white light at an angle, you will see that it splits into a rainbow. You have red at one end and you have blue at the other one. The same phenomena which creates rainbows after the rain is responsible for the splitting of light. And why does it happen? It's essentially because light is made up of many wavelengths. Each component it a different amount as it moves from one medium to another. The scattering is more for the blue light, which has a smaller wavelength, and red, which has a smaller one. So the same thing can be done by using a grating, by some, it's called the diffracting grating. If you take a CD, you must have seen CDs in your homes. And if you focus light on that, you will see that you see a rainbow there. So you can create these spectra by either using prisms or you can by using diffraction gratings. And what Raman said was there were some basic questions which Raman tried to understand and answer. And the questions are very simple. Sea is blue. And he realized that the shorter wavelengths get scattered more than the longer ones. And the blue light has a shorter wavelength, while the red has the longer one. So red light gets scattered the least, while the blue one gets scattered the most. And as the light enters the Earth's atmosphere, there are dust particles around which scatter this light, and the maximum scattering is done to the smaller wavelengths, which is blue, and hence you see the blue color. And the same phenomena is happening with water in sea. As this light goes into water or a fluid or any medium, it interacts with particles, which is the medium is made up of, and the light gets scattered. And the blue gets scattered the most, leading to the blue color. And you remember that the color in light essentially is the wavelength of light. One of the slides got missed out. Okay. One of the slides got missed out. Basically, so what is light? Light is an electromagnetic wave, and you have variations in the electric field and the magnetic field, which propagates the light. So you have light essentially is an electromagnetic wave, and that portion of electromagnetic radiation which our eyes detect is called light. But the other components which we do not see by our eyes are categorized as infrared or ultraviolet or X-rays, gamma rays, and so on. So using the works of Raman, we can have a lot of applications which we can build out of it. Raman effect is used in medicinal tablets. Raman effect will show that chemical composition, distribution, purity of a raw material. So if you pass a certain wavelength of light through a medium, and if that medium is doped or it has impurities in it, then the scattering would be different from what a pure material would do. So this could be used to see purity of a raw material, and this is used in creating medicines. You have to be very specific, very controlled in what proportions and in what amounts we are using different chemicals to create drugs or medicals. It is used in detecting bombs, hidden substances, hazardous chemicals, gases, and so on. It is useful in finding the composition of cancer tumors, right? So the scattering which a normal tumor would scatter light in a do it of cancer and detecting the composition of the tumors and other things. It has been used by NASA in Mars mission recently. You must have heard of which, and they use the Raman effect to look to understand the chemical composition of the soil, of the atmosphere, and other things on Mars or on Moon or any other place. It is also used in archaeology to find out materials and its details. It can be used in cosmetics. It has been used to identify the quality of diamonds. So it has which have become very essential for our health and our livelihood. to securities where we can be using to detect bombs and hazardous substances, right? So it is up to your imagination how you can use this phenomena and use it. I will draw your attention to what spectra does in astronomy and what is the information which we can get when we are studying stars. So if here's a picture uh, of a of a patch of sky from a dark night, and you can see lots of stars in this picture. And what do we notice here? Probably you can notice that certain stars are brighter while the others are fainter. And the other thing which is striking is the colors of stars are different. Certain stars look bluer, while some look yellowish, some look white, some look reddish, right? And this has a lot of information, and there's much we can say about stars from the little amount of lights which reach us. And essentially, it's the light from stars which we have been studying over centuries to understand not just what these stars are, but to understand how whole universe and to understand how the whole universe has evolved. Right. So, why are the stars? What you notice are some stars are brighter and the others are less brighter. And the term which is used to denote brightness is luminosity, right? So scientifically, if you want to use the jargon of science, you say a star is more luminous, or the other one is less luminous. And what is the reason for the luminosity of star? There can be two reasons. A star can be brighter because it is hotter than the other, right? So if you have two stars, one which is hotter and the other one which is less hot, then the one which is hotter will appear more brighter. Second thing uh, could be the size. You may have two balls of the same size, two uh, planets or two stars of the same size, of the same temperature, but one is much larger than the other, then your brightness goes up. The third thing could be a star may look brighter to us because it is closer to us, while the other one is further off from us, right? So there are three basic features which you can attach for why stars are brighter or less brighter. One, the distance to us. From brightness, we can make out how far an object is and how far it is. Secondly, we can make an estimate of their temperature. And third, it also talks about the size. So for a long time, people thought that all stars were of the same sizes and the same temperature. But in present times, we realize it is not so. And here are the which you might have seen through various forwards which we have uh, in WhatsApp and various resources which we have on the net. And what we realize now is the stars come in a variety of sizes and a variety of colors. For example, if Wolf 359, which you see as a small dark maroon ball in the picture on the left hand top picture, then the sun is as big as what it is shown here. And Sirius, which is the brightest star which you see in the night sky, is much bigger than our sun. If you reduce Sirius to the size of a pea, which you see in the second panel on your right, then Arcturus is much bigger than what Sirius is. You see the same panel, Arcturus is, and Aldebaran is much bigger than Arcturus is, and so Sirius. And further, if you reduce Aldebaran in the lower left-hand bottom panel, Aldebaran becomes the size of a pea, and Antares is much larger in Betelgeuse, and the scale goes up. And further, when you have Betelgeuse looking as small as a tennis ball and say the panel on the right hand bottom corner, Then mu Cepheids is larger than, much larger than that, and VV Cepheids and YV Canis Major, right? So these stars come in a variety of sizes, and they are at different temperatures. So the color of a star, the ones which are you see Sirius, it is looking blue in color, while Wolf 359 looks, you can see that Sirius is much more hotter than the Wolf is. And it is not just the size which defines the temperature, but it is basically the processes which are going inside the star, what is creating the heat in a star, which is responsible for the color. For example, you have Aldebaran, which is much larger than Sirius, but it is you are seeing it as an orangish reddish color, which implies that Aldebaran is not as hot as Sirius is. So stars come in a variety of sizes, and they come in a variety of temperatures. The temperatures can range from, say, 3000 Kelvin at the photosphere to about 40,000 Kelvin, right? So they come in a variety. And the color of the star is what tells you what the temperature of the star is. So if you take the spectra of a star and you see the peak where the thing is peaking, where the maximum amount of color is coming. So you focus the telescope to the object and you pass it through a spectrometer and you look at the spectra and study it. By looking at the spectra, you can make an understanding of what is the temperature of the star from the color of it. And the stars which you see in the right hand panel, it is peaking in the ultraviolet, right? Indicating it is a hot star. Which you see on the left hand side, this star is a cold star and it is peaking somewhere around 1000 degrees and so on. Yeah? It is peaking somewhere at 3000. So it varies from 3000 to about 40,000, and spectra is the key to understanding the temperature of it. So here's the picture of the electromagnetic radiation. It defines what we are actually seeing. So the go to the radio regime and you slightly to shorter ones you get microwave, then you get the visible red down to blue, and as you go from blue all the way down to X-rays and gamma rays, your wavelengths decrease and the energy increases. So they are high energy ones, but okay, so the temperature is the key to temperature is the key to the color of it is the key to the temperature of the star, right? So here we see at what wavelengths you get different colors, and all the stars emit in all wavelengths, but they peak at certain wavelengths, and that peak comes from what is the maximum source of heat and what is the temperature of that. Okay, so those which are peaking, like a sun peaks is somewhere around 6000 Kelvin. That's why you see it as a yellow star. Yeah, so this is what is done. You take the light from a star, and sometimes the light passes through a cloud, interstellar cloud. They can be different regions in between the stars, which there could be clouds there, and as the light passes through these clouds, the light gets scattered. and depending on what is the composition of the cloud, it gets scattered by different amounts, and also depending on the chemical composition of the cloud, certain frequencies are absorbed, right? And when you look at the spectra of that, you see them as black lines. So this is called the absorption spectra of a star. And by looking at these dark lines which you see here, you can predict what is the chemical composition of this cloud, right? So when this was the technique it was used to understand the atmosphere of Venus or various planets. So you take the sunlight passing through the atmosphere, and you collect it and see which are the absorption lines which you see. So similarly, sometimes what happens is because of presence of hot uh, uh, chemicals in the cloud, the light, it gets enhanced. Certain frequencies, the photons, they gain energy from those things, and you see it as an emission spectra. The lights, instead of becoming dark, they start appearing as more fluorescent lines. So this is an example of the spectra of a star, and you see a lot of dark lines here. And each chemical element, you get the absorption line specifically at a specific location. Like for sodium, you get it somewhere here between 570 and so on, right? And similarly for ferrous lines are here, and titanium oxide are here, magnesium. So by looking at these absorption lines, you can predict the composition of the stellar atmosphere, and also the strength of the line. If the line is very dark or very faint, it indicates the abundance of that material in that medium. So spectra and this scattering phenomena, which was studied by Raman, plays a very important role in understanding stars. And once you understand the temperature and you understand the chemical composition, you can also predict how will the stars end up, how long have they lived, how long will they live, and how will they die. So the spectra reveals the surface temperature of stars. It reveals to us its chemical composition of stars. Uh, and uh, um, and by plotting stars on the basis of their temperature and their brightness, you can make an estimate of how stars will evolve, and how long will it take for them. So the stars which we see are in a continuous process of being formed. They live to their middle age, they live for a certain time, and they die off. So by looking at the position in this diagram, which is called the Hurstville-Russell diagram, we can give an estimate as to how long a particular star on this will live before it blows up as a supernova. So my time is running out, so I will just give you one last application of how spectra is used in astronomy. Spectra is used to even estimate and understand that our universe is expanding. So what was done was, this is a picture of Edwin Hubble. He, with his assistant Hummerson, they looked at the spectra of galaxies. Galaxies are large collections of stars, and the light of these galaxies will pass through the spectra of these things, of these objects. In the spectra, the lines, say hydrogen absorption line, comes at different locations. So you have a line which should come uh, exactly at a certain point, which would indicate that there is hydrogen there, but it gets shifted by a certain amount. If it gets shifted towards the right side, then you can estimate that the objects are moving away from us. And if the line gets shifted towards the blue end, then you can say that the object is moving towards it. So by looking at the shift in the spectral lines, we can estimate the velocity of the objects. So what Hubble and Emerson did was they realized that objects which are further off, they are moving faster than the things which are close by. And basically the idea is something which can be explained by the Doppler effect, which we very often notice. When there is a ambulance approaching us, we see a high-pitched sound, while if it is receding from us, then you see a low-pitched voice. So when you see the shifting of, when you see these lines shifted towards the red end, then the objects are said to be receding away from us, while the ones blue shifted, the frequency becomes shortened. So, for example, here is a spectra of a hydrogen lamp, which we can have a hydrogen lamp, and in a laboratory through a spectroscope see where the hydrogen line comes, and it is coming very close to the 650 nanometers. Right? The same kind of hydrogen, if it is in some interstellar cloud, like in the Orion Nebula, you see a similar line there. Line indicates the presence of hydrogen. There's no other chemical which can create this kind of an absorption line. And what is happening is hydrogen, you see dark lines appearing in the spectra. And you will see that I will move this across, and you notice that this line is shifting towards the redder side, to a higher end that is on the right side, and objects, while galaxy UGC 12915, which is further off, this line is shifted away towards the reddest, right? And here's another one. So I'll run it towards. This is a closer, and the red line is somewhere near 650. A further object, you are seeing the red line shifted to the red. Hello?
Sir, you're audible now. There was a
You
little
hear-
lag in between. We are audible now.
Look, at what point did you lose the connection?
Sir, we were talking about there is evidence of how the universe is expanding, and you were talking about the various galaxies and also the shift in the red line.
Achha, fine. So essentially, most of it you could hear, because the internet here seems to be unstable. And I just got rebooted.
Yes, so that is what we heard, sir, that how we are able to find the evidence that universe is expanding, how some galaxies seem to be receding away, and how some are, kind of closer to us.
Hello?
Yes, sir, we are able to hear you.
Yeah. Okay. Yeah, so maybe we can
I request the students to be kindly be patient. Sir is having some technical difficulty, looks like. So kindly stay logged in. Okay. I hope you are following the conversation and the concepts taught to you. Yeah. Thank you so much, Pran. Priya ma'am, you're on mute. Priya ma'am,
I'm unmuted now. Yeah. So actually, there seems to be some problem on the Zoom. I'll just try to connect onto that. But till then, I at least thought I'll put it on my phone. So yeah, so hello everyone. And I'll be talking today about the Indian space program. Now, all of you all are aware of the space program. And India is one of the few countries. There are barely 5 countries which have a proper space program of their own. And we are proud to have our own space program. And obviously, the space program has many uses. It's used for various purposes, from ranging from defense to looking for minerals, for weather forecasting, for various purposes, right? But today, what I would be focusing on is the use that it is made in astronomy. In astronomy, why is the science program useful to us? It's connected on that. Yeah. So why is the space program useful to us in astronomy? And I don't know why I seem to be having a problem on my laptop, but just a minute, we'll just sort it out. Don't worry. So should I leave it? Yeah. Zoom into my normal Zoom. Just open that. I'll keep the video on through my phone. Give it to me. Yeah. So, yeah. Okay. Problem. I'm sorry. There seems to be a problem with the net over here. Don't use that. 1 minute. Can you give me the link for this? The link. Okay. I'm sorry, but there seems to be some issue with this. I will just.
Fine, ma'am. We'll just wait for a couple of minutes. So please take your time to set it up. No problem.
Okay, no problem. I don't know what has happened, but okay, here I can maybe put it on. There seems to be some net problem. Yeah, so we'll just stop for. You are signed in there or what? Because then here it's signed me out. So we'll just stop that live stream. Can you stop it? Should I log in from here or no?
Login period.
Then double login, that's not allowed.
It's not locked in here. I don't know what it is.
I think just reboot that system. Let's come on. It says